now we come to materials for energy. And Professor Ravi Silva, Director of Advanced Technology Institute at the University of Surrey, is our next speaker. That's an interdisciplinary research activity with over 160 researchers, and he also heads the Nanoelectronics Centre within the Institute. His research has resulted in over 450 presentations at international conferences and over 400 journal papers. He is the winner of awards from the Institute of Physics, Electrical Engineers, and most recently gave the Clifford Patterson Lecture at the Royal Society on Carbon Electronics. His research interests encompass a very wide range of activities, including nanoelectronics and renewables. And today, Professor Silva will talk about novel semiconductor hybrid materials for photovoltaics and some of the other material innovations in the energy sector. Ravi, good to see you.
Good afternoon. Good afternoon, everyone. Thank you, President, for that introduction. I must start off by thanking the President and the Academy for organizing these lectures, this series on innovation, which has been splendid. I hope I can do justice within my talk to say something about the case study in energy that we've been working on. I think it's not complete if I don't start by reprimanding our keynote speaker, Mark, by saying, Mark, you stole my thunder. But I shall try to do justice in terms of where the green energy challenges lie and materials for energy. Now, you don't have to think back much or look around you to realize that there is a problem. Energy is a strange commodity, as you'll see later on, and as Mark indicated. You just have to look outside the window on a nice sunny day, and it doesn't actually have to be sunny for you to have energy around you. Light is energy. So it's one of these strange conundrums where normally the price of things go up if the supply is low. In the case of energy, it actually is not the case. And that's what I'm going to try and convince you. So looking around you, we've seen the gas prices, the electricity prices rise. Earlier on in the year, you've seen the petrol prices rise. Whenever you get your gas bill, you have a green tax, green levy associated with it. Some of you would say, well, is it actually useful? Is it doing something? And you know you really are in trouble when the church starts talking about this and saying the politicians must do something about it. Now, this is even without considering some of the potential issues associated with the use of fossil fuels. We've seen the thunderstorms in the UK and currently in the Philippines. And some would say that there is a connection between these changes in the weather and CO2 emission. And one thing is for sure is that the CO2 emission does play a role in the climate, and how significant a role is something that is being debated significantly at the present time. And there is also a view that there is a significant amount of correlation between your CO2 levels and the temperature rises, looking at it in a much more global time frame and in terms of a large number of years. So the big issue really that I want to address within the 15 minutes I've got is asking the rhetorical question, is supplying the energy needs of the world today, and I mean the world today, a serious problem? Are there other issues that need to be taken into consideration? And what are the solutions, if any? And the key point is, if there is a solution, why are we not doing anything about it? I think Mark indicated grand challenges. I think the grandest of challenges that we as material scientists, as engineers, can contribute to is the energy challenge. We do know that the energy requirements, the energy needs, keep increasing and increasing as the quality of life improves. And this question as to what are the biggest problems faced by humanity was discussed by Nobel laureates. And Rick Smalley, the late Rick Smalley, asked the question, what are the most significant challenges humanity is going to face in the next 50 years? And number one of the challenges faced by humanity was energy. It was not water, it was not food, not environment, not poverty. So if energy is the most significant challenge that people are going to face, what can it solve? If we had unlimited supply of energy, we could probably have clean water, could use desalination quite cheaply if energy was not expensive. You could eradicate disease, immunize world populations, etc. Now, as Mark indicated, at present, the sun bathes the world with around 165,000 terawatts on a daily basis. Now, if you say half of that is reflected, you're still talking about 80,000 terawatts of energy. Current human consumption is of the order of 10 to 15 terawatts. In 2015, that may go up to 60 terawatts. But there is a 10,000 oversupply of energy in comparison to the current usage. If we start looking at the energy supply at the present time, roughly speaking, 80 to 85% is dependent on fossil fuels. We only have something like 15% that is associated with renewable energy. And even of that 15% in renewable energy, less than 0.1% is direct solar conversion. We've got solar farms such as these spreading onto miles and miles in countries such as Spain, Germany, the US. But yet, there is less than 0.1% of the world supply coming from direct solar conversion. So there must be an issue as to why people are still not adopting this technology. And the key issue associated with this is the cost. If I wanted to get energy from the plug point, I can get it at supply point at less than 5 to 10 pence per watt. If I were to try and get it from solar energy, in order to produce it, it's about 60. And once I install it, it goes over $1.6 per watt. So the cost really is the barrier that is preventing solar energy from being utilized at present. So what's the solution? There are a number of solutions that people have looked at. But typically, within the UK, we've generally looked across the channel to see what the Germans are doing because they're good at manufacturing, they're good at making things. And actually, if you start looking at the data coming out of Germany, the German Climate Change Office, their view is by 2100, 80% of your energy will be coming from direct solar. So it's a transposition of what we have today of 80% fossil fuels going on to solar. At present, on a bright sunny day, Germany can be rid of all fossil fuel energy generation. It's always good to have France next door because if you do have a problem in the supply, you can always ask for some of the nuclear energy that's coming there. So there is a stock there. But at present, there are days in which German grid do not need any fossil fuels to operate. So why PV? It's abundant, it's free, direct conversion, minimal carbon footprints, no arable land required, And year on year, there has been a 40% increase for the last decade. So looking at this issue, we then ask, is it a difficult process in order to obtain energy from the sun? So typically what you would have is sunlight hits, say, a semiconductor. That creates some electron-hole pairs. That allows you to convert that light into electricity. And of course, then you need to think about storage. And how much land do you need to produce this amount of 60 terawatts? And this is a thought experiment as to how much land you would need to power the world. And what you see with these red blocks is the amount of land required in the different continents in order to harness enough energy to power the world. Of course, this is hypothetical, and the idea here is that you would have a superconducting grid that goes all the way across the world that allows you to produce this amount of electricity with no losses associated with the transmission process. But the key point is the amount of land you need is not great. So the solution: we need to reduce the cost of solar electricity. Typically at the moment, crystalline silicon dominates. You're talking about 100 micron thick crystalline material. Imagine if that 100 microns was now reduced to 100 nanometers. So just to emphasize that, and this linking of the scales, etc., there's a 1,000-fold decrease in the thickness, 100 microns to 100 nanometers. But in order to absorb the same amount of light, photons from the sun, you need to do something. You need to fool the material, the light, to believe that you've got an optically more dense material that can absorb all of the photons hitting it. So this we've done by putting nanomaterials, and in particular carbon nanomaterials, within the organic materials in order to absorb energy. And the process is such that you can color the solar cells that you have by changing the nanomaterials you have, plus being able to absorb the material, the energy that is coming in through other optical management means, such as plasmonics and other interference systems. So the idea here, as Mark indicated earlier, is a solar paint. And what we are looking at is solutions of materials that can be spread on surfaces in order to produce layer by layer solar cells that can operate. Now these materials, these structures that we are producing are real. And these are some of the spectra associated with the solar cells that we are making at the Advanced Technology Institute at Surrey. So this is looking at the current density that can be sourced at the voltage, and the maximum power point is obtained when you look at the amount of maximum current that is needed at a particular voltage point. To cut a long story short, these materials currently are operating at about 8.5%. These are on 1 square centimeter, and typically you can make them transparent, right? These are flexible materials. So we are no longer talking about square millimeters. In order to get a transparent conductor, Martin spoke about graphene, and this is proper graphene on top of a surface of plastic that you can put in order to get suitable sheet resistances in order for light to go through and for electrons to be collected at that electrode. The world record at the moment is at about 9.2%. So what we need is looking at these innovative materials, being able to design it at the nanoscale, and furthermore, by having nanomaterials within the structure absorbing much more of the energy spectrum than you would normally absorb if they were pure organic materials. So it's a hybrid material system of organic, inorganic materials that, due to the fact that you've got carbon nanotubes in there, these carbon nanotubes have an electrical conductivity that is 1,000 times that of copper, a thermal conductivity that is 5 times better than diamond, 10 times better than copper. And it also has a significant lateral strength that becomes important when you start putting it into composite type materials. So what we are able to show is that you can create superhighways for charge to transfers within your solar cells that overcomes the problems associated with low mobility in plastic materials. Many of you know that if you have plastic materials, you cannot get high charge current through them because they are insulating, they have wide band gaps. So by having less than 1% of nanomaterials such as carbon nanotubes, graphene, incorporated within your structure, you can overcome the problems associated with transport of charge, the absorption, and the small exciton diffusion length that you normally have associated with carriers. So what we are proposing at present is that in looking at solar technology, in the 60s, you had the first generation of bulk silicon materials. That was followed in the 70s and 80s with amorphous silicon. This is the material that you have in your calculators. After that, the third generation was the dye-synthesized solar cells and the organic solar cells that were there. We believe that it's time to have a leapfrog of this third generation in order to improve its electrical transport properties, its absorption, as well as the exciton transport within the structures by incorporating organic, inorganic materials as a fourth generation solar cell material. Interestingly, if you start thinking of solar cell materials, you also start thinking of usage of it. And one of the issues associated with solar energy is that you need to store it. Unfortunately, every time you have a solar cell, you cannot accompany that with this sort of dam so that you can store your energy. So you need to come up with other innovative ways in which you can start thinking of energy storage too. And in that sense, you can start looking at electrolysis, which is another area where material scientists, engineers are innovating, where they're using solar electricity to split water and create hydrogen, and then making sure that that hydrogen can potentially be used whenever you need to utilize the energy that has been created or an oversupply of the energy that you currently have. We've also been doing some work in terms of commercializing some of these technologies. And in terms of being able to produce nanomaterials that are suitable for use with large area electronics, we've created activity Surrey Nanosystems that allows you to start growing carbon nanotubes, graphenes at low temperatures. So technically, we can grow carbon nanotubes or graphene on plastic substrates now with this technology that we have together with the intellectual property that goes with it. And just to show you some images, the height of these structures that you see, this honeycomb structure, is of the order of 100 to 200 microns. Your human hair is about 80 to 100 microns. You see this as a continuous array, but what you have is a dense layer of carbon nanotubes that are of the order of 10 nanometers diameter, connected together and forming this self-assembled structure. And all of this can happen because you put your catalyst at the bottom and you've grown your structures precisely where you want to grow it. And these materials then can be used to create concentrated solar cells where you have the highest amount of density in order to absorb things. So in addition to looking at next generation solar cells, supercapacitors, fuel cells, membranes are technologies that are being examined. So looking at technologies that need to be backed, if the UK wants to be a world-class technology hub, we really need to have sustainable funding that is adventurous, revolutionary, influencing the world, and focused on excellence. And these are things that the Academy believes in, and I believe this is something that we all need to work together to achieve moving forward. So in conclusion, there is an overwhelming need for innovation really to be used to drive the economy. This goes hand in hand in sustainable policy. Renewable energy is important within the energy mix going forward, and we shouldn't just stick to the solid known solution. And generic technologies must be developed and bring all of these parties together. And finally, can humans interact with the earth in a synergistic manner? I believe it can through nanotechnology. And I believe by having material scientists and engineers working together, we certainly will have a happier world. Thank you for your attention.